Welcome to the second presentation in Unit 4 entitled Sigma. You see these are the Greek letter sigma, so sigma, sigma, sigma. This is a friend is someone who gives you total freedom to be yourself, Jim Morrison. So, the learning goals are that students be able to define a system in which momentum is being investigated. So we're going to look at the concept of a system, that you be able to identify the properties of momentum that make it a vector, and that you be able to calculate the total momentum of a system. So here's what we already know. We know that momentum is a product of mass and velocity, and we know it can be calculated using the formula P equals mv. We also know that inertia refers to the mass of an object, where inertia is the tendency of a system to resist motion. We also know that momentum is a vector, which means that it indicates both a magnitude, which is a number, and a direction. So it would include something like right or east or something along those lines. Now, what we learned in the lab, we learned that momentum is a vector, and we learned that momentums can actually be added when the direction is the same. So if you take one ball and lift it up, it's going to strike the rest of the objects with a certain amount of momentum. But if you take the second ball and you move the second ball up so that now there's two balls right here, now you have the momentum of two objects, the momentum of the first ball and the momentum of the second ball. When they hit, they're going to strike the Newton's cradle with twice the original momentum. So momenta can be added and subtracted based on the direction in which they go. So now, a system. The system is the objects that are being observed. So you're looking at a particular system. I could say, hey, I'm interested in this car. When this car collides with this car. So what is the conservation of momentum, or what is the momentum of that system with just those two cars? Or I could define the system as the cannon with a cannonball and say that's what I'm interested in. Now when you have a closed isolated system, whenever we have a closed isolated system, what that means is that there is no friction because there are no outside forces. So there's nothing like wind resistance or friction or drag or somebody coming up and bumping it after the fact. There are no outside forces. Now the system can include as many objects as you want them to, but the more simple the system, the easier calculations are. So now we know momentum is a vector. Momentum is a vector because it includes direction. Mass is not a vector. The reason why momentum is a vector is because velocity is a vector. And what happens as a result is momentum and velocity will always share the same direction. So if velocity is moving to the right, momentum is to the right. If velocity is down, momentum is down. So they share the same direction. So when we talk about the total momentum, we're talking about the momentum of the entire system. So if you have, let's say, two boxes that are moving towards each other, you would look at the momentum of the first box and the momentum of the second box, and you would combine those in what we call the total momentum. When we call the total momentum, it can be symbolized two different ways. The first way is a P with a total. The TOT stands for total. Or you can express it as a sigma P. A sigma P means the combination of. Generally it means the summation of, but summation always makes people think add. You don't always add like we showed in this example. Whenever you have two things that are going in the opposite directions, you wouldn't add them, but you would subtract them. So if you get confused, you might want to stick with P total. I like to use the summation one because you tend to see this term later in math. So it says objects moving in the same direction. When you have objects moving in the same direction, like we have with this truck and this car, not this car, we're going to leave that out for now. When the objects are moving in the same direction, the vectors in the same direction are added. So you have some sort of momentum vector moving this way and some sort of momentum vector moving this way. Because of that, we can actually add these particular vectors together, and we can say the momentum of the truck plus the momentum of the car is going to equal the sum of the momentums. So the total momentum in this particular case is greater than the individual momentums because they're moving in the same direction. Whenever you have objects moving in opposite directions, the vectors in the opposite direction are subtracted. So you see that with a head-on collision. This particular car was moving in this direction with a momentum of, we'll call it PW because it's a white car. And then we'll call this one P, we don't want to call it tan because that sounds like P total, so we'll call it PB because it's kind of brownish. So now whenever you ever have these cars moving in opposite directions, if you're trying to find the sum total of them, because they are moving in opposite directions, you have to subtract them. So you'd say PW minus PB. Now, the total momentum in this case is less than the individual momentums because you subtract them. It says, how can you represent the total momentum in an equation? Now, this is a really complicated equation that has nothing to do with what we're talking about. But how you'd represent the total momentum of an equation would be something along these lines. You can say the momentum is equal to P1 plus P2 plus dot dot dot. And some of you may be saying, well, how do we know it's plus? And the answer is because you always end up adding momentums. It's just whether the other momentum is negative. And if this is confusing, you can kind of just ignore what I'm saying. But let's say that this thing has a momentum of 10 and this thing has a momentum of 5. Well, really, since it's moving to the left, when we have something moving to the left in math, we say that it's negative. So you would add 10 and negative 5. If you don't like that, if that doesn't make sense to you, just forget that and say, okay, well, it's 10 minus 5. But it's the same result. Okay, next it says, how should the momentums of the objects below be combined? Well, if you look, the clay is moving to the right, the box is moving to the left, and as a result of that, you have to subtract these two because they are moving in opposite directions. Next it says car A is traveling at 10 meters per second before colliding with car B, moving in the same direction at 5 meters per second. What is the total momentum of the system? So what I need to do is I need to find the total momentum, and that's going to be car A plus car B. So I'm going to have car A over here, and I'm going to do it in blue. So we're going to have the mass is 1,200 kilograms. We have the velocity is 10 meters per second. And then we're going to change colors, and we're going to go over here, and we're going to say car B. Car B has a mass of 1,400 kilograms, and velocity is 5 meters per second, and it's in the same direction. As a result of that, the equation for both of them is P equals mv. So because of that, I can say, okay, well, the momentum for the first car is going to be 1,400 times 5 is going to be the momentum of car B. The momentum of car A is going to be PA is going to equal the mass times the velocity. So when I get my calculator out, I can say, well, 1,200 times 10 is 12,000. And then I can say 1,400 times 5 is going to be 7,000. So I have 1,400 and I have 7,000. So now I can take these values and I can add them together right here and right there. So you would say 12,000 plus 7,000 equals a total momentum of 19,000 kilogram meters per second, and I'm going to call it left just because it looks like it's left to me according to the original picture. Finally, it says the cue ball strikes the 8 ball which is initially at rest, as indicated by the red arrow. The cue ball rebounds according to the blue arrow. Predict the motion of the 8 ball. Okay, so now if you were to look at it in this particular case, this is a really tricky question because this 8 ball and the cue ball together have no momentum in the y direction. The momentum is 0. The white ball does have momentum, in the x direction. The 8 ball doesn't have any momentum at all, but the cue ball has momentum in this vertical direction. Now when it rebounds this way. So it's kind of kicking the cue ball to the right. So as a result, you can imagine that this is the direction that the 8 ball is going to go, because together the cue ball and the 8 ball have to cancel the right left directions out.